permanganate versus H2C2O4, that is oxalic acid. So we are performing a titration of potassium permanganate and oxalic acid. So as usual we are going to write the aim first, and we are calculating it for we are going to calculate for amount of KNO4 present in 100 ml of solution, 100 ml of KMnO4 solution by using the standard H2C2O4 solution. So remember the procedure, and you can write all of the other things in all by yourself. So as you can see, this is a redox reaction, right, where oxidation and reduction happen simultaneously at the same time. So you can write the principle of the redox reaction, what goes under oxidation and what goes under reduction. You can write them. KMnO4 and K2Cr27 are the best examples of oxidizing agents. So KMnO4 is an oxidizing agent, so it undergoes self-reduction. You can say that, right? What is meant by reduction? It is gain of electrons. And what is meant by oxidation? It means loss of electrons. And H2C2O4, which is oxalic acid, will obviously become a reducing agent. That means it oxidizes itself. It means it loses electrons. That is the basic property of any acid. You can remember that like that as well. Okay, and the aim is over, and the apparatus is same for almost every titration. Here you are going to use heat, so all the apparatus. Okay. Along with all the apparatus, which include the burette, conical flask, pipette to remove the liquid, and you might have a measuring jar, and you will have distilled water, and you will have burette stand, right? Those are the important apparatus that you need, and along with them you are going to need the Bunsen burner here to heat the chemical, which we are going to see further in the procedure. Okay, so now let's look at the procedure. Okay, first of all you are going to wash it. Those are the normal things that you will write. And the KMnO4, it is taken in the burette. This thing is not good. KMnO4 in the burette. Right, just imagine the burette as a long syringe type thing, and the H2C2O4 is taken in the flask, which is a conical flask. So those two solutions are first taken, and then the H2SO4 is added. Right, H2SO4, you can say it is a promoter. It can increase the speed of the reaction, and then it will be heated for 60 to 80 degrees. After heating, it will be titrated, and no indicator is used here. KMnO4 acts as a self indicator. Right, just remember all of this procedure. Alright, we are going to sum it up again. So KMnO4, it is taken in the burette, and H2C2O4, it is taken in the conical flask. And then what are we going to do? We are going to add H2SO4, and then we are going to heat it to 60 to 80 degrees. Right, this is a symbol for heating, and no indicator. It will be titrated, and then the end point is, what is going to be the end point? Colorless to pale pink. Okay, oxalic acid is colorless, and then it will turn into pale pink. That is a very basic titration. Just remember these steps, and you can write all of the things in your room. Okay, coming to the second experiment, what we have is ferrous ion by dichometry. So as the name suggests, ferrous ion means Fe plus 2, and dichometry, that means there is a dichromate ion present. Okay, so dichromate, chromium is here, right? So di means 2, So the chemical is going to be K2Cr2O7. That is the most common oxidizing agent that we discussed earlier. The potassium permanganate and potassium dichromate are the most common oxidizing agents. So we are going to perform a titration between these two chemicals. So we are going to write the aim, apparatus, principle. So for the principle, okay, it is a redox reaction as well. So what is the since KMnO4 and K2Cr2O7 are involved, we can directly say it is going to be a redox reaction. So K2Cr2O7 is going to be the oxidizing agent. So that means it reduces itself, so it gains electrons, and Fe plus 2 is a reducing agent. That means it oxidizes itself. That means it loses electrons. That means it will turn into a more positive ion. So Fe plus 2 will convert into Fe plus 3. This is known as a ferrous ion, and this is known as a ferric ion. Okay, so this is going to be the principle, and let's look at the procedure now. We can write all of those by our own. So first you are going to wash all the apparatus as usual. Okay, I'm going to mention it here just in case. It will make an extra point, right? Okay. Firstly we are washing the chemicals, and after washing the chemicals what we are going to do is the KMnO4 and K2Cr2O7, these all are colored solutions, so these are always taken into the burette, you can say. Okay, and burette K2Cr2O7 in the burette, and the Fe plus 2, the ferrous solution, is taken in the conical flask. And then is there any indicator that needed to be added here? Let's see. Okay, there is going to be an acidic mixture that we should be adding. Right, it is common for both of the titrations that we are performing. So acid mixture. Directly we added the H2SO4 in the first titration. We will come into the calculations later after we completed with the theory part. Acid mixture, it is a 1:3 ratio of you can write this as well, H3PO4, right, orthophosphoric acid I think, or you can normally say phosphoric acid, and H2SO4. H2SO4 is the most industrially used chemical, and it is also known as the king of chemicals. Okay, so this is phosphoric acid. Alright, we have added this acid mixture as well, and we are going to add DPA indicator, which diphenylamine. Okay, and the titration is performed. So the endpoint for this titration is colorless too. Right, all of these are going to stay colorless to blue violet. Okay, so this is a procedure of what you are going to do for the second experiment. And let us move on to the third experiment. These two are single step titrations, by the way, and now we are moving into multi-step titrations now. Let's change the color. Okay, alkalinity of water sample. So this alkalinity means basicity, and so to neutralize the base and to perform the titration you are going to need an acid. So from the acid based titration it is known as a neutralization reaction. You can write the principle to it. Okay, so let's start. So alkalinity, and there are going to be two alkalinities here, partial and total. Let's look at all of those now. Okay, and for the principle you can write the principle of neutralization reaction. Okay, so the neutralization reaction is acid. What is the acid here? We are going to use the sulfuric acid as always, and plus base, which is the water sample, because it was mentioned the water is alkaline water, so we are using the water sample and we will perform the titration. Okay, so that is going to be the principle. And now let's have a look at the procedure. This isn't looking good. Let's take this. Alright, so that's it for the principle. And first you are going to do what? You are going to take water sample. Okay, by the way, this water sample is going to be 40 ml, because for 20 ml the readings are kind of difficult to take, and for all of these titrations that you are performing, we will explain it in the table as well later. It is 20 ml per experiment and it is 20 ml per experiment. Okay, you are going to take 40 ml of the water sample, and then you are going to add phenolphthalein indicator, right? Phenolphthalein indicator, and you are going to titrate it. And again it will titrate it until you will get colorless, and you will add methyl orange, right? After adding methyl orange, it will turn into yellow color. Okay, so there is this thing to remember. For methyl orange in acids and methyl orange in bases, there is a table, and then we are going to titrate it again until we get what? We get pale pink color. So that is going to be our endpoint. That is it, right? Okay, phenolphthalein, we get pink. Here we get pink, and we are going to titrate it against the acid solution until we get the colorless. And then we note down the readings, and then we add methyl orange and we get yellow color, and we are going to titrate it until we get pale pink color. That is the end point. Okay, so that is it for the third experiment. Now let's look at the fourth experiment. The theory it can be written, but for the calculation you need to look. So we will get into that again later. Okay, complexometric titration. It is known as complexometric titration because a zinc complex is formed here, right, of zinc. So it is zinc versus EDTA. Okay, that is basically the titration, and you are going to write all the steps. First step is the standardization of EDTA. By known zinc. So it is pretty simple. You take EDTA where in the burette, and you take zinc, known zinc, in the flask, the conical flask, and what you do is you add EBT indicator. Okay, so after adding EBT indicator, it gets wine red color, and after you perform the titration, and from wine red it turns to blue. That is the endpoint. Okay, and you are going to take concurrent values and you will get the normality of EDTA solution. And after getting the normality of EDTA solution, you can now do the second titration. Right, you can do the real EDTA versus zinc now. Same procedure. But before, what you did is you did the known Zn SO4 solution. That's why you got the EDTA, because it is a secondary standard solution. The normality of EDTA changes. So you need to calculate what the normality of EDTA is before performing the experiment. That's it. And coming to the fifth experiment, lead acid battery. Okay, so we are going to calculate the strength of lead acid battery, and for that it is also a two-step titration. So for the first step we need to standardize the sodium hydroxide solution. Okay, standardization of sodium hydroxide and OH. And for this complexometric, I forgot to write the principle. Right, so what is going to be the principle? Yeah, so the Zn SO4 is there, right? And it, first of all we are mixing it with erythrone black tea and it get Zn EBT. It is unstable. Okay, and that Zn EBT is getting titrated with EDTA, right? So then we are getting Zn EDTA. Okay, so that is going to be the principle behind it, and you can write it is a complexometric titration. That means a complex is formed, zinc complex is forming, right? You can write what a complexometric titration is and you can write the steps behind it. And you can also write the full forms of these things. EBT stands for erythrone black tea, it is an indicator, and EDTA stands for ethylene diamine tetraacetic acid. Okay, the structure is, that's why I got it out. Most of it is same. There are a few modifications. So you write CH2 and CH2 and you write N C okay, CH2COOH here and CH2COOH here and CH2COOH here, CH2COOH. Tetraacetic acid, there are 4 acetic acids here, and diamine, okay, and there are 2 amines here, and here ethylene. If you check the valency of these things, 2, 3, 4, 2, 3, 4, okay, and 1, 2, 3 for nitrogen, 1, 2, 3 for nitrogen, it's alright. And for C, 1, 3, 4, right, this is going to be the CH2COOH, right, just giving a small explanation. It is like this. So 1 was satisfied here. Okay, I think I need to elaborate it. CH2 and 1 is satisfied here, and COOH, it is a functional group with one valency of 1. So for this C, the 4 are satisfied, And now look at for COH, C H O O. There is going to be a resonance here, as if I know. Yeah. And one is coming out, right? We are correct. Like this, C O O H and another. So it's alright for COH as well. So that is the structure for ethylene diamine tetraestic acid. Just write it this way: CH2, CH2, that is ethylene, and diamine, you are writing for amine here, and tetraestic acid. So CH2COH, you are going to write it 4 times. That will be the formula for VDTA. And now coming to the fifth experiment, finding the strength of lead acid battery. First you are standardizing the sodium hydroxide. Okay, for the finding strength of lead acid battery, first we are going to standardize the sodium hydroxide, NaOH. For that, why are we standardizing the sodium hydroxide? Because we don't know the normality of sodium hydroxide. So titration is being performed, NaOH versus oxalic acid. Right, it is taken where? It is taken in the burette. No, this is taken in the conical flask, just like we did it in the first experiment. Conical flask, and NaOH is taken in the burette. And are we going to add any indicator here? Okay, we are going to add the good old phenolphthalein indicator, I think. Yes, we are going to add the phenolphthalein indicator. And then we are going to do the titration again after we finding the end point. We are going to perform NaOH versus lead acid with same setup. Okay, after that we will find the strength, the normality of lead acid, and from the normality we can find the strength. So that is all about it for the 5 titrations. And now we will look at the calculations. Coming back to the first experiment again. So what was the first experiment? H2C2O4 versus KMnO4. And always remember, the amount of formulas for us is limited. I am writing them here. N1V1 is equals to N2V2, that is the most important formula for us. And after that we are going to use another formula, that is we are getting the weight, right? So normality into gram equivalent weight into volume by 1000. This is going to be another formula for us. So this is the formula that we are going to use for the first titration, second titration. Okay, and we have something else for third. We are going to use it for fourth titration as well. And this formula we are going to use for first, second, fourth and fifth as well. Okay, just seeing the importance of these formulas here. And for the third experiment we are going to write quantity, right? So the units of normality are normal, by the way, and the units of weight are grams, and the units of alkalinity are milligrams per liter. Okay, so those are the units, just remember them. and volume of H2SO4, it is all dependent on H2SO4 formula, by the way. And normality of H2SO4, you don't need to calculate the normality from this formula. It was already known before. The normality of H2SO4 is given to us in the question by 0.02 or 0.01 something, and gram equivalent weight of CaCO3, because we are calculating the amount of CaCO3 present. Okay, and the gram equivalent weight is 50, by the way, and volume of water sample into 1000. This is a slightly different formula that we use only for the third experiment. And for the fifth experiment, the strength is, it is a single line formula. Okay, equivalent weight into N3. Just you are going to multiply with the normality after performing the two-step titration. The equivalent weight of lead is 49. We are going to look at all of these constants. I'm just telling the formulas by the way. So what you do is, in the first experiment, H2C2O4 versus KMnO4, it is a simple one-step titration. You are going to apply the formula N1V1 is equals to N2V2, and from this you are going to calculate N2 is equals to N1V1 by V2. So the N1 is generally traditionally taken of the quantities that we are known before. So the N1 is normality of what? The standard solution here is KMnO4 solution. No, we are estimating the amount of KMnO4 solution here. So the standard solution is oxalic acid. So we are taking the normality of oxalic acid, and the N2 is automatically going to become KMnO4, and the V1 for the N1 is taken oxalic, so the V1 is going to be taken oxalic as well, and the V2 is KMnO4. So the constants, the table is going to be like this, by the way. The volume column, okay, the serial number column will be here, and burette, there is going to be initial here and a final reading here, and then we are going to have the volume again. First, what are we going to take in the conical flask, that is the 20 ml. You are going to write them down here. So here what are we taking? For example, we are taking H2C2O4, so you will write that here. And what are we finding the volume of? We are finding the volume of KMnO4, which is in the burette. So you are going to take 20, 20 and 20. You are going to do it 3 times, and the initial is 0 ml, 0, and the final, the amount will be taken, the final it will be recorded, and whatever you write in the final, the volume also you are going to write the same. So this is how a sample table is going to look like. This is the same sample for all the experiments, 1, 2, 3 as well, right? Yes, 3 is the titration as well, so all of the experiments are going to have the same table. Okay, so that's about the table. And coming to the calculation again, so you are just going to use your Casio and substitute the values. For example, I am taking some sample values here. The N1, the normality of H2C2O4 is given to us as 0.01, and the volume is given to us as 20. No, it is not given, we have taken it here, right? And the volume that we have found after 2 consecutive values, I found it as 20.6. okay, and if you calculate all of this, you will get the V2. Now, sorry, the N2. What is going to be the normality? If you calculate this, you are going to get 0.0097 something. So this is going to be the normality. And after that, you are going to substitute the normality in the second formula. Okay, normality into gram equivalent weight into V by 1000. The V is taken as 100 ml because we were asked to calculate the weight for 100 ml, right? So the normality is 0.0097 and the gram equivalent weight of what here? KMnO4, because that's what you are calculating, right? You found out the normality of KMnO4 and now you are calculating the normality, I mean the weight of KMnO4, that's why you are using the gram equivalent weight of KMnO4 and the volume for 100 ml by 1000. This is the formula. Okay, instead of I will write the answer and we will cross check it with Casio. 0.0306. We should get something like that. Let's see. Okay. 0.0097 times 31.6. These are the constants that you need to remember. And 100. Okay, 30. If you know 30 point, what did we get here? 30.652. If you do divided by 1000, you got 0.0306. Okay. So that is how you do the calculation. That is how you are going to do for all the 3 experiments. I mean all the 5 experiments. And now I am going to write the important constants here before we wrap this session up. Okay, so gram equivalent weight of what is the first experiment here? KMnO4. That is 31.6. That is important constant that you need to remember. And for Fe plus 2, the gram equivalent weight is 27.9. 31.6, 27.9, and the alkalinity of water sample. Are there any constants? Yes, you need to remember the normality will be given and the gram equivalent weight of H2SO4. You need to remember that. The normality of H2SO4 will be given and the gram equivalent weight of CaCO3. That's the base, right? Alkaline sample. Alkaline samples contain carbonate and hydrocarbonate ions. HCO3 and CO3 ions, right? So hydrocarbon ions. And the gram equivalent weight of calcium carbonate is 50. And from the 4th experiment, that is a zinc complexometric, the constant that you should be remembering is this thing. Okay, and for the zinc we are here again 32.69. And for the 5th experiment, lead acid, here equivalent weight, right? 49. So you can see there is a correlation 31.6, 32.6, 50, 49 and 27.9. You can remember these things easily, and all the calculations and the calculation table procedure things will be completed easily. All the best guys for tomorrow's exam and have a great day. Bye.